You can see it is an cyclic esters. Generally, when you take ester, you treat with lithium aluminum hydride, the reducing agent. You get pair of alcohols. Okay. So in this, we treat it with lithium aluminum hydride. To that, we are reacting with chromium trioxide in the presence of H plus. We know it is Jones reagent. And you are doing an excess acetylation as well. Okay. Now in this case, when I'm treating it with at first I'm having this, I'm treating with lithium aluminum hydride. So lithium aluminum hydride will reduce the esters to alcohol as we mentioned. Don't remember that, ma'am, you said it's alcohol. So what are the products that you're going to have right now here? So look at the possibilities of the choices that you're having here. Tea is soluble in hot aqueous NaOH. This is a base. So the one that is getting formed, if it is an acid, it will be yes. It will be soluble in hot aqueous NaOH. They're giving a molecular formula. You can see O4 is there. So I understand it should have 2 moles of carboxylic acid related compounds should be there. And U is optically active. So definitely if it is going to be having chiral carbon as well as if it is not having plane of symmetry, no POS, then it should be optically active for us. And V is giving effervescence with sodium bicarbonate. Definitely, if it is having carboxylic acid unit in it, we have learnt it already. When I'm having carboxylic acid unit in it, the carboxylic acid will react with bicarbonate to release carbon dioxide from sodium bicarbonate. So these are the following set of choices we are having. Okay, pa?
Yes.
Yes. As we mentioned, you're going to have 2 moles of diol. That means this is also becoming alcohol. This is also becoming an alcohol for us. So OH, this is also an alcohol, and I'm having CH3 here. So this is U. Now this U is being treated with Jones reagent. So we know very well if I'm treating it with Jones reagent, the primary alcohol will get oxidized into an acid. Okay. So this is V for us. V will generate effervescence on treatment with aqueous sodium bicarbonate. Yes. V as carboxylic acid unit in it, it will do it. Okay, we are looking at U now. U is optically active. So look at the compound we are having here. C, this is H2OH, CH3, CH2OH here. So looking at this carbon, 2 hydrogen, not chiral. Looking at this carbon, 1 CH3, 1 H, same methyl unit. Okay. Let me go for the second point of difference. CH2OH, CH2OH, again no difference. So you cannot be optically active. because this carbon is also not chiral here. So you can't be there. This can be. Then what else? I'm having T is soluble in hot aqueous sodium hydroxide. What is T for us? This is T, right? Will it be soluble in hot aqueous sodium hydroxide? That means if OH minus is able to react with it, yes, it would be soluble. I can see OH minus is a nucleophile which will attack this carbonyl to form this carboxylic acid. So yes, T will be soluble. Children always remember when they say it is soluble, it means it is reacting. It is soluble in hot aqueous. Yes, that's also right. Molecular formula of W is provided to you. What is U for us? This is U. This is our U. Yesterday we were learning about this acetylation reaction. So I'm having COH and OH is there. To this I'm acetylating. So what would have happened? I would have CHOCOCH3, CH3. Here again also again CHOCOCH3, correct? So there are four oxygens as it is provided to you. So options A, B and D are right here. Understood, Ra?
Hmm. Yes, ma'am.
In the last class, I just gave you a glimpse about this Fry's rearrangement. So whenever you are having phenolic esters, why do I call it as phenolic ester? Because I synthesize this from phenol. From acetylation of phenol, I synthesize this compound. This, if I'm heating it in the presence of aluminum chloride, okay, this COCH3 acts as an internal electrophile so that it attacks the ortho position of the ring here, OH and COCH3. If the ortho position is already, ma'am, in this case the ortho is free. If the ortho is already substituted, in that case the product goes to the para position.
Mm. Ma'am, if
Mm.
both orthos and both para, sorry, if both orthos and para are occupied, then no reaction.
No
Right?
reaction. No, yes.
Yes, ma'am.
Right. Yes. Next one is Claisen condensation. The word condensation tells you that removal of water is going to happen. So basically we have 2 moles of esters here. To this I treat it with a base. Usually it would be an alkoxide along with its respective alcohol. Let me take CH3, CH2, CO, OCH3. So this is acidic here. This is a base for us. The base would abstract a proton from this carbon so that it generates a carbanion CH3, CH minus, COO, CH3. Now this again reacts with another molecule of ester. This carbanion attacks it so that this moves out. We get CH3, CH2, COC, O minus. I'm having CH, COO, CH3 and CH3. This I have CH3, CH2, COH, CHCOO, CH3 and CH3 here. Okay, pa?
Yes, ma'am.
Either it could have occurred like this or the negative charge would have went inside to form ketonic as well. This is Claisen condensation for us. So this is my ester part. To this ester, this is alpha, this is beta. So you can see it is forming beta keto esters. The same
Got it.
reaction if it is happening intramolecular way within itself. If it is happening in an intramolecular way within itself, we call this Deichmann condensation. That means I'm having the esters within the same molecule like this. So that I create a carbanion here and it goes for an attack. So you can understand it will form cyclic intermediate. Clear, ma?
Yes.
Asni, did you understand, Ra?
Yes, ma'am.
The other famous reactions regarding the carboxylic acids and the derivatives involves the effective intermediate called as isocyanate, RnCO. So the reaction is Curtius reaction, Schmidt reactions. So basically, we are going to treat the carboxylic acid. In the specific reagent. I have RCOOH. I have treated with NaN3, sodium azide, so that it forms RCON3. This is called as acyl azide, RCON3.
Hmm.
Now, upon heating, nitrogen gas would have left. Okay, so that what happens is this nitrogen is leaving. This R attacks this here. So I have RN RN double bond C double bond O. This is what is called as isocyanate. So this isocyanate is a very powerful intermediate for us. Same isocyanate is formed in Schmidt reaction as well. I have RCOOH plus N3H. which will also form RCON3. This again releases nitrogen to form RNCO. So the way this RNCO reacts with the other compounds, let us take water here. I'm giving you a simple step to remember it. OH and H, that means the negative part gets added to the carbonyl and hydrogen gets added to this NH. So I have RNCOOH. This acid is called as carbamic acid. This upon heating forms RNH2 plus CO2. Since carbon dioxide is a gas and it wants to leave, the following step releases carbon dioxide. Instead of water, if I used Rn double bond C double bond O, I used an alcohol here, OH and R. Just split up as the same way here. ROH will give you RO minus and H plus, correct? So I have OR and H. So the negative part gets added to the carbonyl and hydrogen gets added here. So what will you form now? RNHCOOR.
Hmm.
Understood?
Yes, ma'am.
When we learnt about Hoffman bromamide degradation, there also the intermediate was isocyanate. In that case, here nitrogen is leaving. In Hoffman bromamide degradation, bromine was leaving. Understood, Ra?
Yes, ma'am.
Another reaction which is involving isocyanate as an intermediate is Lawson reaction. There you have RCONHOH here. Upon acylating, from RCONHOCO. R. We know what is acylation, isn't it? That means I'm treating with CH3COCl. Remove HCl and just pair them up. Now when I heat this, RCO minus moves out. RCO minus moves out so that it forms again the same type of intermediate RN double bond C double bond O. Isocyanate is formed. So four reactions where you see this isocyanate is an intermediate. Curtius, Schmidt, Hoffman bromamide, and Lawson rearrangement.
Got it.
So with this, we are completing carboxylic acids and its derivatives. We have dealt about amides, we dealt about the esters, we dealt about the acids. So the majority of the questions from this chapter comes from the acidic trend of carboxylic acids at first. So remember, for acidic trends of carboxylic acid, if it is benzoic acid related, ortho effect is predominant. So any ortho substitute could be donating, withdrawing. They will be very acidic in this pattern. The next question comes from common oxidation reactions and reduction reactions of acids. Like how do you prepare carboxylic acid from an aldehyde and as well as from the ketones? And similarly, what happens when you reduce an acid here, like in the presence of lithium aluminum hydride or B2H6, yesterday we saw the diborane reactions. And the next one is decarboxylation reaction, geminal, vicinal, those kind of questions we have seen already. We understood that beta keto carboxylic acid will be decarboxylated at faster rate. These are the very common questions for us with respect to carboxylic acid related to decarboxylation, also the sodium bicarbonate test. This is quite common. There are several number of naming reactions we have seen already, like where you see this Coles electrolysis reaction we saw. We also saw this reactions. Just now we saw this, when carboxylic acid is reacting with several number of reagents to form isocyanate to give the respected products. Cold Schmidt reaction, where we synthesize salicylic acid. With respect to amides, it is about the dehydration of the amide and hydrolysis of the amide. When I dehydrate the amide, you get cyanide. When I hydrolyze it further, I get acid. So this is common question for amides for us. Hoffman bromide degradation comes as a very important question for amides for us. And remember, amides are less basic because the carbonyl is next to nitrogen, is involving in the resonance of its lone pair. Then we went on for esters, the formation of esters, saponification reaction, mechanism of hydrolysis of esters, acid hydrolysis and basic hydrolysis. We did acetylation reaction of amides. Okay, with this we are moving on to the next chapter, amines or nitrogen containing compounds. So the first thing about amines you have to understand is that basically, yes, I have RNH2 here. This is called as primary amine. And the nitrogen with its lone pair bonded with one R group we call as primary, R2NH, secondary amine, R3N, tertiary amine, R4N plus X minus is called as quaternary amine. Basically, they are called as salts, quaternary ammonium salts. Let us first discuss about the hybridization, their bond angle, and their stereochemistry point of view with respect to amines. So we are looking at methylamine. This is a common name. When I failed in the IUPAC name, I say methanamine. I can see this nitrogen is making 1, 2, 3, and along with the lone pair is there. So 4 hybrid orbital is required. And hence we call it as sp3 hybridized. I'm looking at the next example where I'm seeing a tertiary amine here, R3N. As this group is becoming a little bit bulky, there will be a little bit of repulsion between them because of steric hindrance. So the bond angle should be significantly higher compared to a normal methylamine. That means comparing to primary amine, tertiary amine would have a higher bond angle with this. Consider I'm talking about amine where it is having, this is R, this is R dash, this is R double dash, and it's a lone pair. We have learned a concept called a stereogenic center. If I say chiral center, it should be basically we talk about carbon here, where carbon is bonded with four different groups. What is a stereogenic center? Not typically carbon it is, not typically bonded with four different groups, but if it is having a lone pair, ma'am, and it is bonded with three different groups, it is a double bonded species. Each olefinic carbon is bonded with two different groups. In such cases, there is a difference when I interchange their positions. In the three-dimensional space, when I interchange their position, they take different orientations. In that case, I call it as a stereogenic center. Look at this amine here. It's having three different groups and a lone pair. Definitely all the four are different for me. So yes, this nitrogen acts as a stereogenic center. So if it is a stereogenic center, can I call this amine as optically active is a question. No, you can't call this amine as an optically active species. The reason is that, what do you mean by optically active species? The one which will show non-superimposable mirror images. So yes, ma'am, I am putting it in a mirror. You can see the flip of the lone pair is available here. Yeah, they are becoming non-superimposable mirror image. That means they are enantiomer. They are isolable enantiomeric pairs. So they should be optically active. That is what we expect. But actually they are optically inactive here. But they are stereogenic center. There is no doubt. When that nitrogen is bonded with three different groups and a lone pair, it is stereogenic. But it is not showing isolable enantiomeric pair. So we say it is optically inactive. Why? Why it cannot show this isolable optically enantiomers? Because this flip that you're seeing right now, this inversion that you're seeing right now is very rapid. Because of this rapid interconversion of enantiomers, we are unable to isolate them. I cannot see this is a pair of enantiomer, this is another enantiomer. It's very fast here. Why should it be very fast? Because first thing is that the energy that is required for this transition is very less. The energy barrier is 25 kilojoule per mole. Faster, very faster it flips itself. And this flipping leads them to show this 1 and 2 as well. And this is what is called as invertomers because they're inverting themselves. Because the energy is very less, they are inverting themselves. At room temperature itself, they do this. All right. What else? As we mentioned, this nitrogen is sp3 hybridized. When it is doing this transition, this nitrogen becomes sp2 hybridized. How is that possible? This lone pair that you're seeing right now goes to unhybridized p orbital. I guess you know very well that hybridization itself is a hypothetical concept. There is no evidence at all. It is an assumption. Or maybe because of this, it is becoming planar. If it is becoming planar, how can it be chiral? How can it be showing the proper three-dimensional transition? Not possible. So here, this lone pair goes to unhybrid. Maybe it goes. So I have 1, 2, and 3 bonds that are made, which makes it to feel like sp2 hybridized. When we say it is sp2 hybridized, it is nothing but trigonal planar. Understood, Ra? So we are
Yes,
discussing
ma'am.
about the optical inactivity of the amines. So in first case, we are just discussing about a primary amine basically. And I said primary amine. There is no possibility for it to behave as stereogenic itself. Am I correct? Because it's bonded with two hydrogens. When I am having R3N, ma'am, it is having R2NH, ma'am. There is a possibility for it to show at least stereogenic center if the R's are not the same. But definitely it cannot be optically active. We saw the reasons here. Okay, what about if it is a quaternary ammonium salt? There is no lone pair at all. Because of no lone pair, there is no flip over that's going to happen. Because of this lone pair only the flip was facilitated. Because the lone pair went into the another orbital, making it to show for sp2 hybridization. Here there is no lone pair, four bond pairs are there, so it is of course sp3 hybridization. It will be optically active, unless if the R groups are different. What is the other cases? The amines can be optically active. When it is present in a cyclic ring, when the nitrogen itself is part of a cyclic ring, there this lone pair is restricted to go for a flip. It cannot acquire its sp2 hybridization. So therefore, in that case, it can be optically active. Let us look at this case here. Look at this nitrogen. What are the bonding it has made? R, a lone pair. This nitrogen has bonded with a CH2. This nitrogen has bonded with a CH2 which is bonded with CH3. So four different groups, correct? Three different groups, one, two, three, and a lone pair. So totally four different things are there. So in that case, it can be optically active. What about here? Lone pair, or this is also CH2, this is also CH2. So in this case, even though the nitrogen is available in a part of the ring, it can't be optically active. Understood?
Yes, ma'am.
Ask me, did you understand, ma?
Yes, ma'am.
We are going for the first reaction to synthesize amines here. It's called as Hoffman ammonolysis reaction. Preferably for primary halides, you can do it. I take NH2, amines, I treat it with RBr. You can see it is a nucleophile here. This could go as Br minus, so it could become R plus. So yes, the reaction continues here, so that it is forming RNHR. First step. The reaction doesn't stop here. It is quite complicated because right now I am still having the lone pair. So it can further go for the reaction where it is R2NH. It will become R3N. Still it is having lone pair. Again it would go for the reaction. So that it will be forming R4N plus X minus. So this polyalkylation is a problem for us. So this method is usually not preferred for the synthesis of amines. This method is generally not preferred for the synthesis of amines because it is polyalkylation. Give me a reaction where the same kind of polyalkylation was a trouble for us.
Friedel-Crafts.
Very good. Friedel-Crafts alkylation reaction where you generate. I'm having RX here, which was reacted with the benzene, so that it is forming R. Still one more time, it is a possibility for it to go for again an alkylation reaction because of this activated group. So it goes for polyalkylation reaction. So that's a trouble for us. Okay. The CH3Br is reacting with NN dimethyl cyclohexylamine. We're looking at the nomenclature here. This is cyclohexane. To this nitrogen is attached to this two methyl groups is there. So the same nitrogen methyl is there and another methyl is there. So I call it N, N dimethyl cyclohexyl. It is an amine. Cyclohexyl amine. So this nitrogen is already a tertiary nitrogen. So just as a lone pair, no hydrogens are available for us. So it goes for a reaction immediately to form quaternary ammonium salt. As look at the nomenclature here, the same nitrogen, 3 methyls are there. N, N, trimethyl cyclohexyl ammonium bromide. As I mentioned, whenever it is becoming quaternary salt, what would happen? It would provide you as quaternary amines are there, it would be salt always. The very common quaternary ammonium salt is cetyl trimethyl ammonium bromide. Cetyl means it's a 16 carbon system. 16 carbon system is there. C16 is there. To this, the nitrogen is there, where it is bonded with 3 methyl groups. 1, 2, 3, and one also is went with C16. So you definitely have a positive charge, and bromide is there. It is a very good surfactant. Surfactant is like a detergents. Almost all your Rin, Ariel, Surf Excel, whatever you see, it will be there. C tab will be there. Okay.
Yes, ma'am.
Right. So this was the first reaction, monolysis reaction. The next reaction is Hoffman bromamide, which we have dealt already with Hoffman bromamide because Hoffman bromide helps in the synthesis of amines. Gabriel phthalimide reaction. We have seen this reaction as well, where it again helps in the synthesis of amines. So these are the general synthesis procedures for amines for us. We are going for the nitro compound. The nitro reduction at different conditions. When I'm using it in acidic medium, alkaline medium, and in neutral medium, what are the products that I would get? One minute. I'm having nitro here. When I reduce nitro groups in different steps, the first reduction makes it to go to nitroso, NO group. From NO2, it becomes NO. The next reduction goes for to hydroxylamine, substituted hydroxylamine. You can see the double bond is broken and I'm just adding 2 hydrogens. Hydroxylamine. Again, the reduction happens. The oxygen is removed, it becomes just amines. This is a sequence of the reductions of nitro groups. First reduction, nitroso, second reduction, hydroxylamine. The next reduction makes it to amines here. So when I'm doing it in a catalytic reduction, that means when I'm using it in the presence of nickel, hydrogen in the presence of nickel, nitro gives you amines. Nitro gives you amines. If I'm doing the reduction in acidic medium, then also it provides you amines. So we can understand catalytic reduction and acidic reduction gives amines only. But if I do it in a neutral condition, what we get is an hydroxylamine. If I do it in an alkaline condition, I have taken nitrobenzene here. Okay. In alkaline condition, you can see it is getting converted into azo product. Several products are possible. Either it could give you azoxybenzene, where the N double bond N connected with benzene is available. At this nitrogen is coordinatively bonded to an oxygen. This is azoxy. The next one is common one, azobenzene. N double bond N we call it as azobenzene. The next one is hydroazobenzene. Same azo only, but to this azo, hydrogen is there. The double bond was broken. It's called as hydroazobenzene. Okay. The next reagent
Yes,
that we
ma'am.
are seeing right now is NaBH3Cn, which is a specific reducing reagent here. Whenever you take haldehyde and you treat it with an amine, take haldehyde, you treat it with amine. This is called as reductive amination. The process is called as reductive amination. I take an aldehyde, I treat with amine. So whenever you see the C double bond O and NH2 is there, just remove water from there. So that what is happening? I have C double bond N here. What is the name of this compound? Imine. When I have C double bond N, we call it as imine. When I have C double bond C and N, we call it as enamine. We call this as enamine. So here I have imine. NaBH3Cn is a specific reducing reagent for the imines. Imines can be reduced even by lithium aluminum hydride. There is nothing wrong in it. But it's a specific reducing agent. Okay, for imines. So you could see there is a compound where it is having imines as well as a carbonyl group. NaBH3Cn will selectively go and reduce only the imines here. So I have the C double bond N, just break them up, add hydrogen. So that I form NH and CH3 here. A new amine has got formed. So what have you done? If you want to introduce an R group into an amine, addition of R group into an amine, use reductive amination process. How many carbon you need? That kind of an aldehyde you use.
Yes, ma'am.
When you're having phenyl hydroxylamine, in the presence of H plus, this OH will be protonated, so that there is a rearrangement that's happening here to make an carbonium ion here. Again the OH minus attacks, so that OH minus attacks here, so that this bond goes in and this becomes NH2 again. You will be forming para-hydroxyaniline. We have learned about tolerance reagent already. What are the specific reactants that would answer tolerance? Phenyl hydroxylamine will also give a positive tolerance test. Phenyl hydroxylamine will also give a positive tolerance test. So if it is giving a positive tolerance test, ma'am, it is not a carbonyl, then what does it show? You can see this hydroxylamine was obtained from the reduction of nitrogen compound only. We just now saw nitro compound. Upon reduction in neutral condition, it gave me this hydroxylamine. So I can understand a nitro compound should have been there initially, which undergone reduction to form this. Clear pa?
Yes, ma'am.
Ma'am, I don't
Hmm.
understand why it gives current response still.
The presence of this OH group here, we have learned tolerance will be provided by a terminal alkyne, showing that it is having acidic hydrogen. Same logic is happening here. Terminal alkyne we saw acetal also gives you tolerance.
Yes, ma'am.
Okay. We are going to the next reaction here, which is called as Hoffman elimination, which is just the opposite of what we have learned in Seitzef. For Seitzef, we learned that when you do an elimination, you will be forming more substituted alkene. In the case of Hoffman, we will be doing synthesizing a less substituted alkene here. So how do I start it at first? I take an amine here. I'm going for exhaustive methylation. What is this exhaustive methylation? And that's what you studied in ammonolysis. When you took ammonolysis, what did you do? I had Rx, I treated with RNH2, kept on adding this R to this. Correct? Same thing I'm doing. I'm having RNH2, I'm having Rx here. Keeping on, I'm adding methyl to it. This process is called as exhaustive methylation. Continuously, I'm methylating it. So, two hydrogens are there, and nitrogen also has a lone pair. So, definitely, there is a possibility for me to do quaternary ammonium salt here. So, what you're seeing right now is a quaternary ammonium salt. Nitrogen lost its lone pair. 3-methyl was added. Because of the positive charge, iodide has also got attached to it. Quaternary ammonium salt. To this, we are adding silver oxide here. To this, we are adding silver oxide here. You can see it is aqueous silver oxide. Aqueous silver oxide means Ag2O in the presence of water. So what happens? It takes water to form silver hydroxide, just like any metal oxides. This silver hydroxide, upon dissociation, once again gives you OH minus. This OH minus gets replaced with this iodide to form quaternary ammonium hydroxide. So the moment you see this quaternary ammonium hydroxide, which upon heating, you can understand it is Hoffman elimination. So what should have happened? I have to do an less substituted alkene. Ma'am, why? Why it shouldn't do more substituted alkene? Isn't it the more stable product here? Remember tertiary butoxide. It was a bulky base. If a bulky base was used, what was our condition? Even though you have a chance for preparing more substituted alkene, what will you synthesize? A less substituted alkene. Because it is a bulky base. It itself is bulky. It can't probe inside to abstract a proton. It will wander outside itself because it is very bulky. Same logic happens here. This group is bulky. Correct? So it can't probe inside to create more substituted alkene. In this case, there is no other go. Both are same in whatever way you're going to do it. Okay. Clear, sir? We are just comparing it with tertiary butoxide. Tertiary butoxide is also bulky, it gives less substituted alkene. Quaternary ammonium hydroxide is also bulky. This also give me only less substituted alkene to me. So I'm just heating here, no base and all. I'm just heating it. So what happens? This N plus is attached with alpha. This is beta. Beta hydrogen elimination as usual. So this moves out. So it becomes a double bond and this moves out. So what you're forming is a less substituted product. Remember, Hoffman elimination is anti-elimination. Hoffman elimination is anti-elimination. Here there is no chance for me to say whether it's anti and all because it is just symmetrical here. Only CH2 double bond CH2. In other cases, if it was substituted, there it would be forming E isomer, not Z isomer. It is geometrical isomer possibility if it is there. It would provide me E isomer, Entgen, not Zuzman. Okay, pa?
Mm.
Surya, did you understand, Surya?
Yes, ma'am.
Yes. We'll wind the session with the last elimination, cope elimination. Same only, same type of eliminations of quaternary ammonium salts. But there is a difference here. Just the reverse. This follows shades of product here. That means it will give you more substituted product. Okay. That was anti-elimination. This is syn elimination. So we start with a tertiary amine. I treat this tertiary amine with hydroxide. Look at the previous case. Look at the previous case. It was quaternary ammonium salt. Look at this case, cope elimination. It is still a tertiary amine only, isn't it? Because the nitrogen is not having another carbon. To this, I am treating with hydrogen peroxide. It is an oxidizing agent. It will introduce oxygen. So it is tertiary amine oxide is formed here. This I heated, which is going to form alkene. Okay, which is going to form alkene for us. So I'm seeing it's NH2 here. Let's see an example here. Both Cope as well as Hoffman is happening in thermal medium. That means I heat it above 100 degree. I treat it with amine. It is aliphatic amine. It is a primary amine. I treat it with nitrous acid. What is the first step? Removal of this N2 to make a carbonium ion. Yesterday we learnt it. Now it is primary, ma'am. I am trying to make it still more stable. So this methyl goes for a rearrangement here so that I form a positive charge here. Look at the next step. I have OH minus. So what's happening here? I am having the OH has got added here. To this we are heating it to form the more substituted alkene. Clear till this?